Okay, so we start the next sessions about applications of functional programming. So we will have two talks: the applications of functional programming on computational biology. Okay, the first talk will be given by Höner. We're talking about leaking around concatMap, efficient combinators for dynamic programming. Okay, please.
Yes, thank you. Okay. So, I'm normally doing computational biology. I have a strong interest in Haskell, but I'm not a programming person per se, so this really is with an application. The goal for me was that I want to do efficient dynamic programming, especially geared towards RNA biology, as this is what I'm doing. And the types of problems I want to solve basically are that I have a single input sequence and I write a dynamic programming algorithm that can be transformed into a context-free grammar. So if you are not interested in RNA biology but are interested in parsing and context-free grammars and other types of grammars, this is still interesting for you since it's basically about efficiency of parsing. The next thing is that I don't want to see any explicit indices in there, since index calculations are really easy to get wrong and to introduce bugs. And furthermore, I want to be able to sweat out the semantics or the evaluations of individual parsers quite easily. And this is actually an improvement over what I wrote in the paper already. So, and as a very simple example algorithm, we want to have actually an algorithm that parses input like the input word up here. And let's sneak in a little definition, since our parser has to work on ever smaller or ever larger subwords or substrings. We say that a subword is just a pair of indices ij telling us what the current subword is. So our grammar that we want to consider has one non-terminal s, and we can either parse the empty subword. If we cannot go smaller anymore, we can remove either the left or the rightmost character with a C parser. C parses exactly one character. Or what we can do, and this is kind of special and what we do often, we can say the production S2, C1, S, C2 takes off the leftmost and the rightmost character of our current subword if C1 and C2 are in this small subset. And finally, this is the last production, S2, SS. We want to be able to take our subword ij and try out all parsers where we have a moving index k between I and j, thereby having two independent subproblems that we want to solve. And there's already Rennon's principle going on in there, if you know about this. The second non-terminal C is just for convenience. These are the four characters we want to consider in our input. As kind of a specialty compared to what the CYK normally is doing, every input we can give to our algorithm, if it's composed of our characters, is accepted by the parser, and we actually have an exponential number of correct parsers. So what we want to do is replace each parse immediately with its semantics or with its evaluation. In this case, we want to have a semantics of 2, the maximum number of base pairs. This basically means of all the parsers of our input up here and this grammar, we try to find out how often can we employ this production rule and count the number of times we did it for the certain parse. So if we take this grammar and this semantics or evaluation and rewrite it into our EDSL, okay, the slide is a bit full, but start up here. This is just our grammar we've written. We have our single non-terminal S, and we have a couple of production rules. So we have our production rule S goes to epsilon or E, S goes to C then S. But what we do is we immediately have our functions for evaluating the current production rule empty up to split. So what they do is, for example, in the case of pair, we say that we take a function pair that evaluates a character followed by our non-terminal S, or the ever smaller substring, followed by a single character. And since we want to constrain this parse to only be successful in certain cases, we introduce a constraint up here. This terminator just allows us to define several productions below each other. And finally, since we want to immediately get the semantics of a path in order to have good performance and not have a list of exponentially many paths, we immediately apply an objective function down here, which reduces the many paths we get for each subword to a single optimal path. You can see this up here, that a grammar is actually our non-terminal and a function from a subword to just one optimal path. The second part is just one of the evaluation algebras, which are quite simple. So if we start with empty, we don't get any score. With left and right, we just keep the previous score. With pair, we get the previous score and just score the two characters on the left and the right with some scoring function, probably +1. And if we split into independent subwords, we just add them up. And the objective function is just maximization. And to make this really efficient, we bind to the character terminal, the input, then we have the empty terminal, get the length, say that we want to memorize our non-terminal S using a strict unboxed table, and use a library function to fill everything. And we are done. This is efficient. Now the combinators that we still need are basically just for some syntactic sugar. For example, the percentage operator is just to make Haskell pairs a bit easier to use, so that we get nested pairs if we have more than one symbol, more than one terminal or non-terminal. The application of a function that is variadic actually is a bit more complicated, since we first need to take our nested pairs of symbols, turn them into something that a function called mkstream can transform, give it the current subword index. Once we have created a stream, which if you do not know stream fusion, you can just think of a set or a list of different paths. But this will get us our stream or list of paths. Then we can apply our function, giving us our semantics. And finally, we are done and have a stream of evaluations of the current subword paths. If we do have more than one production, we simply use this combinator, which just says, well, I have a production, which is just a function from a subword to a stream. I have actually two of those, and combine them by applying each of them to the current subword and concatenating the streams that I get of the paths. Finally, applying the objective function is quite easy. Applying the subword to stream function to the current subword index and the objective function, and we get one optimal path for our subword. Actually, writing terminals or non-terminals is a bit more complicated. So if we have this production rule up here, S goes to character followed by S, we write this as seen here, but the left part, left applied to the two symbols, doesn't concern us right now. What this turns into internally is this nested pair. So we have a bottom case, and we have our character into a pair, and then we add the symbol S, and we do have our nested pair. Now the table we actually want to write is some implementation that we don't care about. It works for hashes or databases or whatever you're interested in, so you can write any kind of data structure you want here. But what we need to say is, if I do have a table in the second position of those nested pairs, then I create stream elements, the individual paths, where I do have a stream element at the outermost position, followed by the stream element generated from the inner nested pairs. Then I have my current index and the actual element at the position for my table. And using this, I am actually coming to why I need to sneak around concatMap. The problem is, at this point, I need to create a stream for the inner part X. And let's say X actually passes the subword I to K, and I need to pass till J. So I do have a list of individual paths. Now once I have done this, the current symbol, in this case the current non-terminal, will pass everything from K up to J in some manner. But the problem is, for each path that I have been generating here, there can be many paths created by the current symbol. In this case, the symbol table actually does have a moving index L, which you can see here. And every time I'm moving this index one further to the right, and creating a new path, but the X part stays the same. Writing this using concatMap or similar things, list comprehensions, introduces sums, partially applied functions, whatever you want to have, which makes everything slow. But using the nice stream fusion function flatten makes everything turn into highly efficient code. So, actually using the whole system and benchmarking it, which is what we want to do anyway, since the user just cares about the EDSL and how fast it is, let's take a look. So, we start up here, and please note that the timescale is logarithmic, which is kind of important here. ADP, or algebraic dynamic programming, was the first instance of a DSL for dynamic programming for bioinformatics in Haskell about 10 years ago by Robert Gigerich. Very nice to use, but more than a factor of 100 slower for a typical problem, and we don't want this for high throughput. Robert Gigerich's guys actually thought of a solution themselves. They did write a new compiler, the GET compiler, and a completely new language, the GET language, which takes a description, like similar to the ones that you have seen, and turns it into C++ code, which you can then compile using GCC, CLang, or whatever, and you get this performance curve, about 1.3 seconds for an input size of 1000. I mean, those are just house numbers, but for comparison purposes, it's okay. The nice thing for us is that actually doing this, writing an embedded DSL in Haskell itself, is faster than doing it in C++, with a lot less work, both in implementing algorithms and in implementing the library itself. I mean, this is just higher order Haskell functions that turn out to be quite efficient. So we are actually really good. We need about, this was 300 milliseconds for an input size of 1000. If you try to be better and write it in C, a very small C program, just to test, optimize it as best as possible using standard options, then you are only about 50% faster than Haskell in this case, which basically means that we do have a dynamic programming framework and you can easily separate between grammars. You can try out different things, how to parse your strings or your input. You can try out different algebras. So if you want to rescore some parsers to see if you better match your biological objectives, that's quite easy, and you can just experiment because you don't have this mix of grammar and algebra that is hard to understand and hard to change. We are actually well within a performance of ×2 or ×3 of well-optimized C. We do have examples for more complicated algorithms, like the RNA fold algorithm, which actually has 4 non-terminals and about 20 production rules. And even there, we are about a factor of 2.8 slower only, and this should be able to be improved on. If you want to do certain more interesting things, like stochastic backtracking of your filter tables, you can do this. You can have all kinds of effects. You can talk to things that only work in I/O, since this whole framework is completely monadic, so you can do everything you want to do. And if you want to have constraints, this is quite easy too. You can have simple constraints with filtering, which just means you filter out different parsers based on what your filter allows or disallows. And you can include constraint kinds, which makes it quite easy to say, I have 2 terminals, those supposedly pass part of my input, but the combined size of the subwords does not exceed 30 characters or something, which does happen quite often for us too, but it's really hard to get right if you have many terminal or non-terminal symbols that all have those constraints. Using this approach, you just say locally for each symbol what kind of constraint you actually want to have, and you don't have to figure out what kind of index to look at to determine those constraints. Furthermore, we will extend this whole approach for sparse dynamic programming, meaning that you can actually improve the runtime and the memory consumption of your algorithm without going into heuristics territory, and we will generalize our dimensions, since for the more complicated bioinformatics algorithms, it quite easily becomes extremely hard to get things right. I mean, the RIP algorithm, which just tries to figure out how two RNAs play with each other, already has 66 non-terminals and a couple of hundred production words, and I don't think anybody here would want to check out if all the indices are correctly computed. And of course, if in any way possible, but this is more for the Haskell guys here, I'd actually like to be faster than C, because this would make our life extremely easy, because then we have a good DSL and are faster. Some thanks to Ivo Hofacker, my boss, who lets me do all these things, Robert Gigerich, with whom I'm talking about the future of ADP, algebraic dynamic programming, Roman Lechinsky, who basically answers everything I need to know about stream fusion, so big thanks to you, and the Austrian FWF for funding this project, and a special thanks to 3 anonymous reviewers and 1 shepherd here. If the paper is understandable to you or you like this, it's mostly because of those guys and who gave me great ideas on how to improve the DSL to the current state. Thanks.